work that I did with Ophir and it came out maybe 2 weeks ago. And okay, so the next slide. Yeah. Okay, thank you. So as I said, string theory provides a large number of different low energy effective theories, which have an ultraviolet completion to quantum gravity. And in general, different such effective theories have different properties, like you have different gauge groups, different number of particles, and so on. But there appear to be, at least appear so, some rare features which, as far as we can tell, are common to all the effective theories that we obtain from string theory. Having spotted such features and patterns, it's natural to try and understand whether they have to be that way, whether they're really universal. So this is what the swampland program is. It's motivated by the existence of such universal features, and the aim is to understand if these universal features are always required by any theory of quantum gravity, or more precisely, they are features of any effective theory that has an ultraviolet completion to quantum gravity. So an old idea is that in quantum gravity, there are no U1 global symmetries. So that's an example of a swampland constraint in some sense. There should be no global symmetry. And the simplest argument, I think, for this is that we can consider a black hole, and a black hole there's a no-hair theorem, which says that it does not really reflect any global symmetry charge that it might carry on its horizon. And therefore, a black hole of a fixed mass actually has an infinite number of possible microstates that could be associated to it. It could have any global symmetry charge, and that's in contradiction with the expected finite entropy of a black hole, of the so-called Bekenstein-Hawking entropy. So one way to think about this is the following. You can take a black hole, you can, of a given global charge, throw in some particle carrying a global charge, let the black hole radiate away by Hawking radiation, the mass of that particle. Hawking radiation cannot radiate away, at least as far as we understand, any global charge, because the horizon is not sensitive to the global charge. So there's nothing that distinguishes between positive and negative charges on the horizon. And so you'll just come back to the original black hole mass, but with one more global charge. And that's what we mean by the fact that there could be an infinite number of possible microstates of a fixed black hole mass. And you can rephrase this infinite entropy argument in terms of an infinite number of stable black hole remnants. So the argument is exactly the same as what I just said, except you let Hawking radiation take away the mass of the black hole all the way down to the Planck scale, where we don't know what happens after that. If you want, you can throw in, let's say, n copies of one charged particles, let the black hole Hawking radiate away down to the Planck scale, and by the time you reach the Planck scale, there's no more mass left over of the object to emit the charge back again. You've gotten rid of all the mass, but you've kept all the charge. And so you're left with an object which is completely stable. It's a so-called a remnant. You're left with a stable remnant of the black hole. And because you can do this now with any number with any initial charge for the black hole, you actually have an infinite number of stable remnants in that case. And this infinite number of stable objects is completely analogous to the infinite entropy I just mentioned. It's just that you let the radiation not take you to some large mass, but you let it decay all the way down to the Planck scale. So it's a rephrasing of the infinite entropy in that sense. Okay, can we go to the next slide? Okay, and we can rephrase things again. This time it's not really just a rephrasing, it's a little bit of a different story, but they are really closely related. So I think it's almost a rephrasing. So we had before an infinite number of these stable remnants, and we can understand these infinite number of stable gravitationally bound objects already just by starting not from a large number of particles and letting it decay down, but building it up, starting from a small number of particles. So for example, if you take the particle that's charged under this global symmetry, and you just put it next to a copy of itself, then the particles will attract each other by the gravitational force. And if you think about the mass to charge ratio of the bound state of these particles, it will have the same charge as twice the charge of the particle, but it will have less than the mass of twice the particle because there is a negative binding energy due to the attraction. And it's easy to show that if you have some object and you ask, can it decay to some other objects, then it can only decay to other objects if at least one of the objects that it decays to has a smaller mass to charge ratio than the object, just by charge and energy conservation. And so since the bound state has a smaller mass to charge ratio than the particle, it cannot decay back to the particle. And if that's the only charged particle in your theory, it cannot decay to anything at all. If you have more particles in your theory, then you should just form these bound states with the particle that has the smallest mass to charge ratio in the theory. If you choose that particle and form the bound state, then that bound state cannot decay to anything in your theory. So it's a completely and utterly stable state, and you can just keep building those states up by adding more and more of these attractive particles. And this way you form this infinite number of completely stable gravitationally bound states. If you add enough of these, eventually you'll reach them, the Planck scale and above, black holes and so on, and you'll reach these remnants, but you can build them up already from the bottom up. Okay, thanks. So as I said, this infinite number of completely stable bound states can be, by these change of reasonings I mentioned, these rephrasings, related to this infinite entropy, which we know should not be the case. So this is an argument why we don't want U1 global symmetry. So, okay, so what should we do to deal with this issue? Well, we should gauge the U1 symmetry. And if we gauge the U1 symmetry, then the story changes, because now if you put the particle next to each other, there is not just a gravitational attractive force, but there's also a repulsive force due to the gauge interactions, due to the fact that you've gauged the U1. So now there's something fighting against this bound state. Similarly, for the black holes, you can't just form any charged black hole and let it decay down to the Planck scale, because there is now the extremality bound, which tells you that the black hole will radiate and lose its mass, but no further than the bound set by its charge. It cannot go below that. So again, we see what happens is when you gauge the U1, you find some competing effect that's stopping this infinite number of stable gravitational bound state. But if we send the gauge coupling to 0, then we just recover the same physics again. So the force just goes away, and the bound or the extremality bound becomes trivial. And that's just a statement that if you have a gauge U1 and you send the gauge coupling to 0, you decouple the propagating degree of freedom, but you keep the selection rule. So essentially, you turn it into a global symmetry. So it seems that you can't just gauge the U1, but you have to gauge it strongly enough. So strongly enough relative to what? Well, there's only one other character in this game, that's gravity. So it better be that you should gauge it strong relative to gravity. And I can go to the next slide. So thanks. So that is essentially the weak gravity conjecture. It says that we should gauge the U1 strongly enough to avoid these stable bound states or stable black holes. Now, it's a conjecture, and so it's not it's not a proof that there's something wrong with this, but roughly speaking, the reasoning follows what I just explained. You can start with infinite entropy, turn out to infinite number of stable bound states, and say that, well, the gauging should be strong enough to stop these bound states forming. Yeah, so if you do that, can you go back one slide? Sorry, there's just, yeah, so as I said below, if so, then we must have a charged particle with a mass that's smaller than its charge. So that's what we mean by gauging strongly enough. We should gauge it stronger than the mass of the charged particle, in particular, that's the mass of the particle with the smallest mass to charge ratio. Okay, thank you. So next slide. Thank you. Okay, so then you can now take this logic and you can kind of run with it and apply it in different situations. So one situation you might consider is say, well, okay, so far we just considered the case when there's a U1 gauge theory and gravity. What happens if the theory also has mass to scalar fields? Scalar fields also lead to a self force between the particles, and it's an attractive force between the particle and itself. It's always attractive. So essentially, they add to the kind of gravity side of things in terms of the bound states. And so if we want to keep the same logic, then we should modify the weak gravity conjecture and make it some kind of stronger statement saying that we basically want the repulsive gauge force to be stronger, not than just gravity, but gravity plus the scalar attractive force. Okay, so this is the formulation that's written there. That's the natural logic that follows from this. So next slide. Okay, so, and indeed you can go and test these things in string theory. As I say, these arguments are kind of, some sense, hand-wavy, but perhaps the nicest evidence for the weak gravity conjecture comes from the fact that you can, it seems to be respected in all string theory constructions we know. So here's a nice example. This is a calculation done in F theory of some spectrum of states. And you see there is this red dashed line, that's the mass of these states. And then the y-axis is the charge of these states. And you see that the dots are the states, and so the charge is bigger than the mass, so that's good. And then there's this green dotted line, that's the coupling to the scalar fields of the states. And the blue line is the sum of the two attractive forces, both gravity and the scalar force. And then we see that we still have these states which are repulsive. So the gauge force is stronger than the sum of them. Those are the red dots. And we can see that the spectrum behaves in an interesting way. First of all, we see there's more than one such state. So this is typical. You actually find usually infinite towers of such self-repulsive states. And secondly, we see that the self-repulsive states, the red dots, start at small charges, some charge of order 1. In this case, you see the charge 1 state has a red dot, but the charge 2 state doesn't. So the charge 2, there's no self-repulsive state, but the charge 1 there is, the charge 3 there is again a self-repulsive state, and so on. So what we see is we see an infinite number of them, and we see that they start at some charge of order 1. And you can do this in many, many different settings, and you always find this pattern. So much so that there's actually no violation found to date of the weak gravity conjecture or this repulsive statement. I should say, though, it's difficult to test this in non-supersymmetric settings because it's difficult to find controlled vacua of string theory that are not supersymmetric. And so there is, of course, that factor that perhaps we've been misled by things that are always close to supersymmetry. So, for example, here the states are not BPS states, but still there is some underlying supersymmetry in the background, which maybe leads to this, so we don't know. So it's very good to look for non-supersymmetric tests of the weak gravity conjecture, and that's partially one of the things we'll try to understand. Okay, so next slide. Okay, so this was somehow one formulation of the weak gravity conjecture. Essentially, we asked that the repulsive gauge force, Coulomb force, should be stronger than the gravity plus the scalar forces. But now, if we think about anti-de Sitter space, then so if we think about a particle and its copy, in flat space, we can take them an infinite distance away from each other. And then the only forces that act on them are the Coulomb forces. That's the leading interactions, and everything else just falls away at infinity. But ADS is essentially a box, and we can't anymore take them infinite distance away from each other. We can take them to the boundary, essentially. Therefore, there isn't this clear separation anymore between long-range forces and other interactions. So we should try to reformulate things in an even sharper and clearer way. Okay, so not just in terms of long-range forces anymore. And since we were motivated by forbidding these bound states, it's very clear what the statement should be. We should just straight away impose that. So this is a formulation of the weak gravity conjecture that we propose. Should be true in flat space and in ADS space, but it's really important in ADS space. So-called positive binding conjecture that if you have a weakly coupled gravitational theory with a U1 gauge field, there should exist at least one charged particle in the theory with a charge of order 1, which has a non-negative self-binding energy. Okay, so that means that if you take, if you look at the 2-particle state, it has more mass than twice the 1-particle state. So if the particle was attractive, if we think of this intuition in terms of repulsive and attractive forces, then, as we said, the 2-particle state will have less mass than twice the 1-particle state because you have a binding energy. If it's repulsive, then it's the other way around. The two-particle state has some, you have to work to create a two-particle state, so it's has more mass, and particularly, especially if you put it inside a box where you can't take them to infinity. So this is the formulation of the weak gravity conjecture that we propose, and as I said, it becomes particularly important in ADS because you have to consider not just the long-range Coulomb forces. So let me give an example. Let's consider. So are there any questions now about this? Sorry, this is a good point to stop. Yes. Sorry.
I mean, the way this formulation says there should exist at least one charged particle in the theory, but I mean, doesn't that imply that that particle automatically has to be unstable?
Why?
Well, I mean, if the binding energy is positive, then isn't it always unstable to decay into?
It means that if you take a two states, I mean, it doesn't.
I'm sorry. Yeah. Right. You don't need the charged two state to exist as a particle.
Yeah. The one particle state is a stable state.
I understand. Yeah, I see. Right.
Yeah.
Okay.
If you have many particles, then some of those one particle states might not be stable, but the one with the smallest mass to charge ratio is always stable. Oh. So that's always a stable particle. Yeah. Any more questions? Oh. Okay, so yeah, so let's look at this binding energy in ADS space. We consider, for example, 5-dimensional ADS space, and we can look at this effective theory that of some charge scalar. So this is we have gravity, we have a gauge interaction, and we have a mass and a charge scalar, and then we also have these contact quartic interactions. So these will be important for the binding energy. So if you can go to the next slide, one can calculate the binding energy of two of these particles, and you find three contributions. There's a contribution from the photon and the graviton exchange, which is like what we described already in the long-range forces, but there's also now a contribution from the contact terms, the quartic interactions, because we cannot take the particle infinite distance away from each other, so the wave function overlaps of the two particles. The positive binding conjecture says that then some of these things should be positive. And here I've rewritten things in terms of I exchanged the mass of the particle for the dimension of the dual operator, which will suggest already that there is a very natural conformal field theory dual to this statement. Can we go to the next slide? Thanks. So indeed, the conformal field theory dual to the binding energy is very simple. It's basically the anomalous dimension of the operator phi squared. It's not an anomalous dimension in the sense of the difference between the full dimension and the classical one. It's precisely what I wrote here. It's the difference in the dimension of phi squared minus twice the dimension of phi. That's precisely the dual to the binding energy calculation that I just showed you. And that receives these three contributions. And to be more precise, phi squared is the leading operator in the OPE of phi times phi. And now if we write this relation in terms of the charge of the operator instead of phi itself, then it means that the dimension of the charge of the state of charge 2q, where q is the charge of phi, should be minus twice the dimension of the operator of charge q, should be positive. That's the positive binding conjecture. So that's what we're getting. And then from this, we can formulate, of course, a more general statement. So one can consider, it's called the abelian convex charge conjecture, consider any CFT with U1 global symmetry. Now, at this point, we're still talking about CFTs with weakly curved gravity duals to relate to the weak gravity conjecture, but I'll talk a little bit about generalizing that. Denote by delta Q the dimension of the lowest dimension operator of charge Q, then this must satisfy a convex-like constraint. So that's precisely the generalization of what I just showed with Q equals 1 and 2. So delta of n1 q0 plus n2 q0 should be bigger than delta of n1 q0 plus delta n2 q0 for any positive integers n1 and 2 and some q0 of order 1. Okay, so let's talk about what this q0 is. What is this q0? Well, from the bound state intuition we expect it to be the charge of the operator with the smallest dimension to charge ratio in the theory, because that's what you can form bound states from, completely stable bound states from. And it is also clear that if we define it that way, if we define q0 to be the charge of the operator with the smallest dimension to charge ratio in the theory, then the conjecture follows almost trivially. Because if we take, let's say, we consider the dimension of n q0 divided by n q0, then by definition, this must be bigger than the dimension of the operator charge q0 over q0, since we define q0 that way. And so rearranging this, we just recover, again, this kind of convexity statement. So the non-trivial statement is really the statement that q0 is of order 1. And this is really what is captured this is what's really captured in the weak gravity conjecture. Because remember, if we think of the operator, if you like, the dual field as forming, if it could form bound states, then each time you form a bound state, you decrease the dimension to charge ratio, but you increase the charge. So that means that if you could form bound states, the operator with the minimum dimension to charge ratio would be something at very large q. Okay, because you can always just throw in another one of these particles, and this would just decrease the mass to charge ratio. If we are saying that the operator with the smallest dimension to charge ratio is some q0 of order 1, then that means that we are imposing a weak gravity conjecture. So that's really what we're saying. And now we make this wild leap in the language of my collaborator, and we say, well, there isn't, if this thing was to be true for any quantum field, for a conformal field theory that has a weakly coded gravitational dual, it's not clear that those CFTs have any kind of sharp separation from other CFTs in the general space of CFTs. And therefore, it's natural to propose that if it's true in all those CFTs, perhaps it should be true in all CFTs. Whatever the mechanism responsible there could be true everywhere else. And one clue towards that is that we're able to formulate it in a way which seems to have no problem handling would-be gravity duals of theories that are not weakly curved in the gravity side. So for example, some weakly coupled CFTs are expected to have gravity duals with an infinite number of massless high spin fields. And then it wouldn't really make much sense to compare gravity and the gauge field, because they're both just part of some infinite tower of high spin fields. So they're not particularly distinguished. But the formulation makes no reference to gravitons or gauge fields at all, and can handle this kind of dual theories with no problem. So at least that's perhaps a clue that perhaps it could be quite general. So yeah, so this is the idea, and of course we can formulate it. We don't know how to prove it or even generally motivate from the CFT side, but we can of course test it. That's something we can do. Before testing it, we can formulate a more general version, so-called convex charge conjecture. So let me just state it. One can consider any CFT with a continuous global symmetry group G, and consider a simple factor G0 inside G, and then donate by delta R the dimension of the lowest dimension operator in the representation R of G. So R is like the analog of Q. So then there is always some representation R0, which is the analog of Q0. Okay, so R is like Q and R0 is like Q0, and which is non-trivial in G0. So it should be charged under this factor of the symmetry we're looking at, and has weights of order 1. So that's the analog statement to Q0 being order 1. And such that the dimension delta Q, defined as the dimension of the symmetric product of Q symmetric product of R0. Perhaps it's a bit misleading. We shouldn't have called it Q. Perhaps we should call it N. So that's like the analog of taking N times Q0. Okay. Should satisfy convex-like constraints. So delta of N1 plus N2 should be bigger than N1, N2. Okay, so this is just a completely natural generalization of the previous statement for U1 to non-abelian theories, where we replace Q0 by some representation R0, and we replace N times Q0 with the nth symmetric product of that representation. Okay, so before we go on to testing the conjecture, are there questions about this formulation and about the general motivation? I
have a question.
Yes.
Is it possible to extend this idea to, say, to a CFT deformed by an irrelevant operator? That is some theory that flows to a CFT in the UV.
I think at the CFT point it should be okay. I mean, so we are somehow assuming that any CFT has some, it should be true for any CFT. So I don't see why not.
Well, no, beyond the CFT. If you deform the CFT, because your holographic argument seems to suggest that it could work for any background that is asymptotic to ABS, not only.
Right. I think that's a very good question. I do not know what happens if we deform away. It's like asking also the analogous question, how does weak gravity conjecture behave in non-homogeneous backgrounds in some sense? I do not know what happens if you deform the CFT and to this statement, and I think that's a good question. I do not know the answer.
Well, as far as the anomalous dimension, since it depends on the UV properties of the theory, it will not change. So the inequality will hold even after the deformation.
It depends what kind of operator, I guess. Like we said, if it's operator sensitive to the UV, then you're saying it's should still be okay. Yeah. I don't know. The statement we made is just for CFTs, but as you say, it's plausible that starting from a CFT, one can deduce some statements for other CFTs that come from it. Yeah.
Okay. Thanks.
But that's a quantum field theory question. I mean, once you start from the CFT, if the anomalous dimension is convex to the CFT, you can then ask in quantum field theory, would it still be convex under certain deformations, and that would follow. Yeah. Okay. Are there any more questions? All right. So this is the argument for the conjecture, and now we can talk about tests of it. So when we talk about tests, let us first of all think about the general picture for CFDs. Can this thing even make sense generally before we even talk about specific theories? So one thing, of course, that this conference is about is that at large charge, for sufficiently generic CFDs anyway, the spectrum is actually convex. It goes as a power of Q with some positive coefficient, where Q is a power bigger than 1. That means that it's convex. And that means that if we take Q0 to be sufficiently large, then we expect the conjecture to be true. Okay, so in that sense, what we need to really test are situations where the large charge behavior has not been reached yet. Once it's reached, then we're okay. But that's good, because that means that Q0 is somehow bounded from above, which is what we want if we propose that it should be of order 1. So that's a good thing. Other kind of theories we can consider are supersymmetric theories, and we consider BPS states, or equivalently we can also consider free scalar theories. And then in both these cases, the behavior of the operator is the same. It's marginally convex. It's linear in the charge. Okay, so that's still okay. So BPS operators, supersymmetric theories also seem fine. Also free scalar theories. Another thing we can say is consider two-dimensional CFDs, and then a U1 global symmetry implies actually two such symmetries. There's a left-moving and a right-moving symmetry, and we can choose to gauge one of the two. And if we do gauge that, then we yield a so-called coset CFT. And if we look at the spectrum under the other U1, the one we didn't gauge, the one that's still a global symmetry, then it behaves in this way. It has some contribution from this coset CFT plus some contribution with some parameter A that's positive times Q squared, which is convex. So it always has a convex contribution plus a contribution from this coset CFT. And if the CFTs is actually a direct product of the left moving and right moving, then you can always take the identity operator in the coset CFT, and then it's automatically convex. If it's not, then we assume, and as far as I understand, it's generally the case that for some charge of order 1, you can choose this to be the identity operator, and then the spectrum is convex. So it looks like in 2 dimensions, there's somehow strong general evidence for this, but of course, it's still not a proof. So I talked about free scalar theories. What about free fermionic theories? Then it's actually quite nice because the spectrum is then not even marginally convex, unlike for the scalar theories where it was marginally convex. At least if we take Q0 to be equal to the number of components of the fermion, which is obviously some order 1 number. And this is because of Pauli's exclusion principle, which requires derivatives to be inserted into operators. If you try to build up the charge, you put in more and more of these fermions, then you need to put in derivatives because you can't put 2 powers of the same Grassmannian variable in. And if you put in derivatives, you increase the mass, but you keep the charge the same. So you work in more and more towards convexity when you put derivatives in. So for example, if we look at 3 dimensions, free fermionic theories of 3 dimensions, the spectrum looks like this. This is the mass of charge 1 is 1, the mass of charge 2 is 2, but the mass of charge 3 is 4. So we see already it's not convex. So 1 plus the charge of 1 and the mass of charge 1 plus the mass of charge 2 is not even marginally equal to the mass of charge 3. So it's order 1 difference. And because it's not even marginally convex, that means that if we do any small perturbation of this theory, so any kind of small parameter perturbation of the free theory, which is so any kind of perturbation theory, will maintain convexity. Because it's just going to give us a small correction to something that's not even marginally convex. And so any weakly coupled, not just coupling, but large N or any kind of small parameter controlling a fermionic theory will have a convex spectrum. The only way out of this is if you have a very large number of fermions, so that you delay having to put in these derivatives in. So for example, if you have some fermions that carry color and you look at large N, then you can try to avoid this way out. So any theory with an order 1 number of fermions that has any kind of control over it will satisfy the conjecture. So that's a good thing. It's a good check. Yeah, please feel free to interrupt if there's any questions. If we now try to look at testing explicit theories, so specific theories, then we can, typically that means we have some parameter by which we can control the theory. And if we have some parameter, then there is some sense of weak coupling, whether it be large N or perturbative couplings. And then we can really assign specific operators to the charges. So there's some field phi, and we can define the convexity as the difference between different powers of phi. So the dimension of phi to the n1 plus n2 minus the dimension of phi to the n plus the dimension of phi to the n2. So for example, that should be positive. That's a way to formulate it here if you refer to fields instead of charges. Okay, so we go to the next thing. So this is what we'll try to calculate. So the simplest theory we can try to calculate this at is at the Wilson-Fisher fixed point for U1 theory in 4 minus epsilon dimensions. So this is the theory here, and this has this fixed point. Now, this is not really a vigorous test of the conjecture because the theory actually contains non-unitary operators. But it's a good test in the sense that, first of all, at least for epsilon equals 1, you do get a unitary theory. And secondly, it's not clear exactly what aspect of, we will show that some non-unitary behavior can violate the conjecture for sure, but we don't know exactly what aspect of non-unitarity is associated with the conjecture, and in that sense, these are interesting things to look at. So if we ignore this issue about the non-unitary operators, we can calculate this in perturbation theory. So actually, it was very useful because there were a lot of papers in the last 2 years which calculated these things for us. I didn't realize it was only in the past 2 years that these things were really calculated, these higher operators. I guess in response to the large charge paper, so people started calculating these tests, but it was of course very useful because we could just read off the results, and this was calculated, and indeed you find that this is positive for small in the epsilon expansion. Now this is really an expansion in epsilon times n, and it's true for small epsilon n. if epsilon n is large, then you go into the large charge regime, and then we know the spectrum is convex anyway. So that's also okay. And one can check that, in fact, it remains convex for any value of epsilon n interpolating between the two, at least using the large n expansion. So you need some kind of parameter. So this seems to be okay. One can consider now an ON quartic model in 4 minus epsilon dimension as related to the previous one. Now we take the field to be the fundamental of ON, and you look at symmetric products of it, and that's what we mean by these N1 and N2. And one again finds this positive behavior as we did before. You can look at the U1 and ON sextic models in 3 minus epsilon dimensions. One again finds positive behavior. There's a slight subtlety here. If you look at the sextic model, the leading term is a 2-loop term, and it vanishes when N1 equals N2 equals 1. So certainly for N1, N2 bigger than 1, the spectrum is convex because you see this positivity of the leading term. You can ask, is it fully convex? So is it convex for any N1 and N2? So for Q0 equals 1. The statement is yes, but you have to go to next loop order to be able to check that. And this, luckily, there are these results of this 4-loop order by Jack and Jones. And we can just use those, and we can check that indeed the spectrum is convex. So it's fully convex. So Q0 is equal to 1. Yeah, so, and it's also true for the ON models. I think this is the U1 I've given here. Oh no, maybe it's just for the ON actually, yeah. So it's generally true. So can we go to the next slide? Okay, so that was using epsilon expansion. You can also use the large N expansion to analyze these kind of theories. So this is nice because now you can really go to integer dimensions and look at unitary theories. So you can look at the ON quartic model in 3 dimensions. And you see again the spectrum is convex. You can read it off in this case because it's a scalar operator, so it's marginal. So the only thing you need to check is the sign in front of the first nonlinear contribution. So that's, in this case, it's the Q squared, and the Q squared has a positive sign. That means that the spectrum is convex. You can formally calculate for the ON quartic model also in 5 dimensions. And then, interestingly, you find that it's not convex. So you find that the coefficient in front of the Q squared term is negative. So this violates the conjecture. And similarly, you find non-convexity for the ON quartic model in 6 minus epsilon dimension. And but it turns out that these theories are non-unitary theories. So there are operators that you can find that lead to the theory to be non-unitary and have complex coefficients. And there is something quite interesting here because the non-unitariness actually only shows up non-perturbatively in N. So you don't see it in perturbative expansion in N. On the other hand, the non-convexity shows up already perturbatively in N. So if the conjecture would be true, it would be very interesting because it would somehow know about this non-perturbative non-unitariness, or if you like, you could tell that these theories would be non-unitary already perturbatively using the conjecture. On the other hand, it doesn't mean that the conjecture might be difficult to prove perturbatively, in a sense that these theories look like perturbatively they're okay, and yet they violate the conjecture. So these are interesting things, but they are not counterexamples. They are non-unitary theories, and so that is fine. Next slide, please. Okay, so another thing you can do is look at gauge theories. So far we looked at non-gauge theories, and now you can, of course, first thing you want to do is do some kind of perturbative calculation. And so you can consider, let's say, 4-dimensional SUNC gauge theory with NF massless fermions and NS massless scalars. This has a perturbative, so-called, Banks-Sachs type fixed point for large N, large number of matter. And because you have scalars, you also have these marginal operators, quartic scalar operators that I've written down here. And the fixed point has to be a fixed point of everything, of the gauge coupling, but also of these H and F tilde, of the coefficients of these marginal operators. And there is such a fixed point, and that's very nicely shown in these recent papers. And what we can consider, for example, are scalar mesons that are charged under this SUNS global symmetry. So we can consider something like phi star phi. So not phi dagger phi, that would be a singlet under the flavor group, but instead we want to take two different flavor indices in phi star. So this is some non-trivial transforms some non-trivially under the flavor group. In fact, it would be in the adjoint. And then the nth power of it would be in the nth symmetric product of the adjoint representation of SUNS. So this is the kind of things we're looking at. So meson operators like this. And then we can calculate the leading, so the 2 meson operator compared to twice the 1 meson operator. That's going to give you
not really. I guess.
Sorry?
It's recommended, but
I didn't know if maybe they changed the things because of the new wave or something.
Sorry, what is the question? Is there a question?
Sounds like maybe someone was accidentally unmuted or something.
Okay, they seem to be conveying some strong opposition to the. Okay, all right. So
that's okay. We muted the opposition. You can go on.
Okay, yeah, you can the dictatorship. So okay, yeah, so we can calculate the 2 meson operator, take away twice the dimension of the 1 meson operator. That's the test of convexity. And because it's a perturbative theory, essentially, if that's convex, the whole spectrum is convex, because that's like the leading behavior. And we did this calculation, and what we find is that the convexity parameter goes like A, where A is some positive number, times the sum of these 2 coefficients in the quartic terms, H plus F. And then one can show that at fixed points, the sum of these things is indeed positive. And that's related to the boundedness of the scalar potential. It's like if you have negative terms in the scalar potential, then you'll just get a runaway and there'll be no vacuum to the theory. So the positivity is essentially the statement that there is a vacuum to this theory, and this is equivalent to convexity of the spectrum. So indeed, it passes this test. One can also calculate the fermion meson operators, but then it's a much more subtle calculation and much more difficult, and we haven't done that, but it can be done in the future, hopefully. Okay, so let's look at yet a different class of theories. So we're looking at different classes of theories and therefore different ways to calculate these anomalous dimensions. So in this case, we're going to consider strongly coupled gauge theories, and we're going to use semi-classical methods to calculate the dimension of operators. So we're going to consider a 3-dimensional UNC gauge theory with NF fermions, and this flows to a CFT in the IR. And this 3-dimensional theory has a global U1 topological symmetry. That's basically the one whose current is Hodge dual to the field strength of the gauge field. And the operators charged under this global symmetry are monopole operators. And at large NF, the dimension of these operators can be calculated using semi-classical method. And this is the results that they find. So you see here the charge and the dimension. And you can just look at the first terms on the left, that's the large NF contribution, and you can see that the numbers are convex. So if you take the dimension of charge 1 plus charge 2, you find something that's less than the dimension of charge 3. Or if you like, if you take twice the dimension of charge 2, you find something that's less than the dimension of charge 4. So this is a convex spectrum again, consistent with our conjecture. So next slide. Thanks. So one can do similar computations now instead of fermions taking scalars. And with the scalars, you can also have quartic terms and in 3 dimensions, or with or without the quartic terms. And if you have them or not, then these are what are called the CPN models and the tricritical models. And this is the spectrum of monopole operators in this table that I have on the left for the 2 models. And indeed, you find for both of the models, the spectrum is convex. You can check that. And one can look also at fermionic theories, but now with quartic couplings, so like Gross-Neveu type quartic couplings. And this was also calculated. And again, one finds that the spectrum is convex. This is the kind of the red dotted line on the figure on the right. The blue one is the pure QED one, which is the one that we had in the previous slide, fermions. There's also some other, I think, theories that were calculated in these papers that were also found to be convex. A qualitative change you can do to these theories, you can add Chern-Simons interactions, and you can have them at level k. So now you have another big parameter, another parameter in the theory that you could try to play with to try and validate the conjecture. But in fact, one finds that the monopole spectrum becomes more convex monotonically as you increase the Chern-Simons level, as you introduce Chern-Simons interactions. So the most marginally convex, so the strongest tests of the conjecture are actually for 0 Chern-Simons level. So, so for any of these Chern-Simons modification of these theories, one just finds that convexity still holds, no matter what the Chern-Simons level is. So that's yet a different qualitative test of the conjecture, and it also passes that one. Okay, so the next slide, please. Okay, so actually in all the examples I gave so far, we found that the full spectrum was convex. So we could take Q0 equals to 1 in the series. So is that always true? So here we give an example where you cannot do that. You cannot take the lowest charged operator. So one can consider a single chiral superfield with a superpotential that's cubic. And in 3 dimensions, this flows in infrared to some interacting fixed point. In 4 dimensions, it's infrared-free fixed point. We can also do it in 4 dimensions, but 3 dimensions is a little bit neater. Then you have since it's a symmetric theory, you have a U1R global symmetry, and the operator phi is BPS. And since it's BPS, that tells you there is a certain relation between the mass and charge of that operator. So you can look at the scalar component of big phi, and this has charge 2/3. It's just because the superpotential has charge 2, so this has charge 2/3. And then since it's BPS, the dimension of it in 3 dimensions is exactly equal to its charge. And so we can normalize the charge to be integer to match our formulation of the conjecture by multiplying it by 3. And so we see that the dimension of the charge 2 operator is 2/3. But we can also look at a fermion in the multiplet, and the charge and the U1R of the fermion is 1/3. And so if we normalize it, that would be charge 1 by multiplying it by 3. But the dimension of the fermion is 7/6, since the scalar plus 2 fermions should give you dimension 3. That means that the dimension of the charge 1 operator is 7/6. So then this is clearly not convex for Q0 equals to 1, because twice the dimension of the charge 1 operator is bigger than the dimension of the charge 2 operator. So that's not a convex spectrum. But if we take Q0 equals to 2, so we look at the scalar piece, then the spectrum is convex, and it follows very naturally from the BPS bound. The phi is a BPS operator, but phi squared isn't, and all the other phi's are not. And therefore, by the BPS bound, that means the delta of 2n, so the charge 2, but to the n, is bigger than n times delta of 2. So if we take Q0 equals 2, then that's okay. So we restrict into the scalar pieces, then we're fine. But if we allow scalar and fermion to mix with, if we look at convexity, then it's not convex. So you can't look at convexity mixing the 2 different spins. So all our examples are consistent with a strong version, with 2 strong versions of the conjecture. One is that Q0 is the charge of the lightest charged operator under the U1. And another one is the Q0 is the smallest scalar operator charge. So the smallest charge of scalar operators. So everything seems to be consistent with these. And these are basically duals of strong versions of the weak gravity conjecture that was studied for many years. And in flat space, there are proposed counterexamples to these in supersymmetric theories, but in flat space and with multiple U1s. So the multiple U1 statement is slightly different. It's the statement that if you have multiple U1s, then it's not true that if you choose any ray along the lattice of possible charges, then the smallest charge along that ray satisfies the conjecture. But if you project everything down to a single U1, so if you look at single U1 examples, there is no counterexample. So it may well be that it's true. So we don't know, but everything we've checked so far is true with these stronger versions. So these are good things to try and check. So one nice check you can do of these is in completely strongly coupled theories. So remember what I said, that because of the large charge behavior, we expect a theory that is completely strongly coupled, so with no big parameters, to always be convex for some Q0 order 1. Because large charge behavior kicks in at something of order 1, since there's no other big parameters in the theory. And when you get large charge, it's convex, so it should be fine. So something that we can think about, for example, is the O2 model in 3D. We know from general large charge arguments that we expect the conjecture to be true for Q0 or some order 1 number. But you can ask, are these stronger versions true? Is it true that the full spectrum is convex? Can we take Q0 to be the lightest charged operator or the smallest charged operator for the scalars? And it turns out that in these theories, one can also calculate the spectrum, and it is convex fully. So starting with Q0 equal to 1. Another nice thing to note about this is that you can actually calculate these things from bootstrap methods. So bootstrap bounds typically only give you a lower bound on the dimensional operators, but sometimes you can get actual, you can really get the dimension out, and that's nice because perhaps then bootstrap could be used to as a way to try and prove the conjecture or test it. And there's also another nice comment to make about this. This theory is proposed to describe the superfluid transition in helium, and so some of these things can actually be experimentally measured. In this case, actually, if you see in this table, the thing that's experimentally measured is the singlet under the U1, but it's plausible to expect that maybe the first, at least the leading non-singlet term could be experimentally measured. I don't know if the second one can also be measured so that you can really test convexity experimentally, but it would be very interesting if that's possible, because if this conjecture was really true, then in principle it should hold, I guess, for any kind of phase transition that should be described by some relativistic CFT, even if we don't know what that CFT is. So in principle, you could even check the conjecture experimentally in that sense. It could make experimental predictions, even when you don't have an underlying CFT theory to describe it, if the conjecture is correct. So I think that's a very tantalizing possibility. I don't know if it's practically possible or not. So the next slide, so that's the end of the talk, I think. So to summarize, we propose that the natural formulation of the weak gravity conjecture should be in terms of a self-binding energy of the particle. And this leads to a very neat and simple CFT dual statement, which is that the spectrum of charged operators should be convex. It seems to hold in all the examples we tested so far. In the absence of any general argument or proof of this, we need to keep testing it. That's what we do, and or try to prove it. And if we keep testing it, we should look for counterexamples to it. And if we do find counterexamples, try to understand what is special about them, and try to understand about this more about convexity. I think that's an interesting thing to consider. And I mentioned this tantalizing possibility of experimental tests of the conjecture, which I think is very interesting. That's it. Thank you, and thank you for managing. Thank you, Susanna, for managing the slides. I apologize for the technical problems. Okay.